Everybody. So today we are going to start a new chapter. This is chapter 29, sources of magnetic fields. We already mentioned at the beginning of chapter 28 that we can have either a permanent magnet, but we have also mentioned if a current passes through a wire, it also generates a magnetic field. So this is it's a given nowadays, but this is actually was an invention. So we will speak about how it was discovered. Okay, we will speak about the Biot-Savart law, which is the law that tells us how we can determine the magnetic field that is caused by a current flowing through a wire. We will speak about the magnetic force between two parallel conductors conducting currents either in the same direction or in opposite direction. We'll speak about Ampere's law, okay, and the magnetic field in a solenoid and a toroid, and we will speak about Gauss's law in magnetism. So this is quite a lot of concepts to cover here, but we have only 1 week. Most probably will not be able to finish this week. Probably it will take us to next week. Okay, so let me first of all start by showing you this video. All right, so let me start it. Let's stop it first. Increase the volume. Volume is maximum here, it's maximum here. Okay, bring it back a little bit. I don't know why the volume is quite low. Let's see.
So the magnetic field went from pointing to the north to pointing.
Okay, let me start this again.
Runs north-south. When I close the switch, I'm going to...
So here he has a wire, and he has batteries. So when he connects the wire to the batteries, the current will flow through this. These are compasses, and you can see that all the needles of the compass, when there is no current flowing, they are pointing to the north direction. Okay? So when he closes the switch, the current will pass through this wire, and we'll see what will happen to the needle. Okay, so observe now.
Create current that goes through this copper wire and through our complete circuit. Notice what happens to the needle when the switch is closed. All 3 compass needles deflected toward the east. So the magnetic field went from pointing to the north to pointing to the east. When I open the switch and turn the current off, the magnetic field goes back to its original orientation. So the compass needles face north again due to the Earth's magnetic field. Now,
so this is evidence that the current flowing through a wire generates a magnetic field that affects the compass needles. Okay, so this was an invention. Ørsted was actually doing teaching like I'm doing now, and he was using current, and he by chance he observed that when the current is on, he observed that the compass needle changes direction. Okay, so he started investigating this, and later on they found out that the current flowing generates a magnetic field. Notice what will happen next.
If we place the compasses above the wire instead of below, and we close the switch and run current through the wire.
So now he's placing the compasses above
Notice
the wire.
what happens. This time the compass needle's deflected to the west. So the magnetic field above the wire faces one direction, and the magnetic field below the wire faces the other. So above the wire it was to the west, and below the wire was to the east. This is how Michael Faraday and Hans Christian Ørsted determined that the magnetic field circles the wire.
So there is a
because if it circles the wire, it points
the wire.
one direction below and one direction above. This discovery paved the way for the invention of electromagnets, the telegraph, and the DC motor. Common bar magnets or permanent magnets don't have an on-off switch. These magnetic fields have an on-off switch. Turn on the current, we turn on the magnetic field. Turn off the current, we turn off the magnetic field.
Okay, so very nice illustration that a current current flowing through a wire generates a magnetic field. And as he mentioned, this invention actually, or this finding, I guess, led to many other inventions later on. And now currents flowing through magnetic fields are used in many devices, included, for example, the magnetic resonance imaging machine. The MRI machine, if you go to the hospital and they ask you to do an MRI for example, a knee injury or anything in the body, this here gantry has a magnet that has a wire, a superconducting wire that conducts high current and generates very strong magnetic field. And this magnetic field is about 3 Tesla in some machines, and it can reach up to 7 Tesla. And this magnetic field is used for imaging the anatomy of the person. So it's a very important machine that is used very commonly in diagnosing different diseases. Okay, and the nice thing now is this is not, first of all, it's a very strong magnetic field that we can generate. Second, it has a switch on and off, so you can switch it on and off. Unlike a permanent magnet, the magnetic field is always there. You cannot turn it off or on. Okay, so Hans Ørsted, who was a Danish physicist and a chemist, he discovered this in the early 1800s, and so basically he observed the compass needle deflects when it is placed close to a wire conducting a current. Okay, so here we are showing a wire that is not conducting current, and the compass needles are all pointing in the north direction. Okay, as soon as the current is on, okay, the current passes through the wire, then you can see that the needles are aligned in such a way they make a loop around this current. So this indicates that the magnetic field is actually, or the magnetic field lines are circular in shape, so they're around the wire and they are circular. So the unlike the previous magnetic field lines we saw for a permanent magnet. Remember, for a permanent magnet we said the magnetic field lines, they go from the north pole to the south pole of the magnet, and they stop there. Here, these magnetic field lines, they do not have an end or a beginning, so they are circular in shape. Okay, so let me go to the presentation mode and okay. All right, so actually this figure here shows iron filing. These are, if you take iron and you use a piece of paper, you get iron filing. and you place it around the wire. If the wire is conducting the current, you will see them aligned in such making like circular shape paths. So this is indicating another illustration of the magnetic field due to a current flowing through a wire. Okay, so after this, in in 1800, Jean-Baptiste Biot and Félix Savart, both of them are French physicists, mathematicians. They performed experiments, quantitative experiments, to determine what is the strength of the magnetic field due to an element. So if you have, for example, an element ds and the current flowing through here, and if you have your point P with a distance r from the element of current to this point here, this is a unit vector r. So they performed experiment and they found the following observations. First of all, that B is perpendicular to both ds and r. So here we should say bs and r. Okay. So this is the r vector, the ds vector. The magnetic field is perpendicular to both vectors. So this is the plane, and the magnetic field will be perpendicular to the plane. Second, the magnitude of the element or magnetic field vector is inversely proportional to the distance squared. So if you get close to the wire, the magnetic field is strong. You get further away from the wire, the magnetic field is weaker. Okay. Also, they found that the magnetic field is proportional to the current that is flowing through the wire and to the magnitude of ds of the length element ds. So also, so it's proportional to the current in the wire, and it's also proportional to the element or this current element ds. Okay, so they must have trying to think how they can do this measurement without the effect of current of the other elements. So they must. So how to make a small element ds if the current is carrying the wire? One has to go back and see what, how did they do that. Okay. The magnitude of the magnetic field is proportional also to the sign of the angle theta. The angle theta is the angle between the wire element s and the unit vector r. So this is the angle theta. So taking all of these observations together, mathematicians, they are mathematicians, and they came up with the equation, and this is the called Biot-Savart law. Okay, so they determine that the magnitude of the magnetic field due to an element ds is given by mu 0 divided by 4 pi. Mu 0 is a constant, times the current I, times the cross product between the element ds and the unit vector r. The unit vector r has a magnitude of 1 and joins the current element ds with the point of interest p divided by r squared. So mu 0 is called the permeability constant, and it's given by 4 pi 10 to the minus 7 Tesla meters per amperes. Okay, so basically if you write 4 pi 10 to the minus 7 and you divide it by 4 pi, the 4 pi's will cancel and you will have 10 to the minus 7. Okay, I is a current flowing through the wire, r hat is unit vector from the s to the point of measurement, r squared, r is the distance between the point P and the segment ds. Okay, ds is a length vector. The magnitude is the length of the segment, and the direction is the direction of the current. It's like we had before. Remember, we did the force on a current conducting wire. We said is IL crossed with B. So if a wire is conducting current is in a magnetic field, it will experience a force given by this. So here we define the length vector L, which has the length of the wire, and the direction is the direction of the current. So this is the same thing, ds, okay, except now it's the current that is creating the magnetic field. In the previous chapter, we had a magnetic field. We did not know what was causing the magnetic field. Maybe it's a permanent magnet. If you pass a current in a wire in a magnetic field, then it will experience a force. Here, we are saying that if a current passes through the wire, this current will generate a magnetic field around the wire. So this is very different from what we have seen in chapter 28. Okay, so we can, if we write the cross product as the magnitude of the S times the magnitude of the unit vector R, which is 1 times sine of the angle between them, we can write the magnitude. So the magnitude dB is mu0 over 4 pi. So I ds sine of theta, where theta is the angle between the two vectors. It's the smallest angle that they can make. So it cannot be this angle here. So this is angle phi. We use the smallest angle, which is in this case theta. Now, this is the magnetic field due to a small element, the S. How about if I want to determine the magnetic field due to the whole wire? So what you can do, you can start adding the magnetic fields, summation of these vectors, and if you make the element ds very small, this summation becomes an integration. So this is the magnetic field produces at point P by the whole wire. So in this case, you basically do the summation or the integration of all of the magnetic field contribution from each small element ds in the wire, and you get this integration. So it's the integral of mu0 over 4 pi I ds crossed r crossed with the unit vector r divided by r squared. Okay, so this integral in certain situations might be easy to perform, and we can calculate the and we will do a couple of examples using this integral. Okay, let's do this checkpoint. All right, and let me go for the Kahoot. So enter the Kahoot number. Three 8674115. Okay, so let me post the question. Okay, so here we have an element ds with a current I flowing through this element. Okay, and consider the magnetic field due to the current in the wire as shown in the figure. Rank point A, B, and C in terms of the magnitude of the magnetic field that is due to the current in just the element length ds shown from greatest to smallest, or to the least. So we have point A along the line. We have point C at this location and point B, and we want to rank them, the magnitude of the magnetic field due to this element. All right, so I'll give you 30 seconds. Yeah, so this must be wrong. Cannot be fake. Okay, can we start? All right, so let me start. Make up your decision. Is it A, B, or C? Okay, 1, 2, 3, and we'll start. Five seconds. Okay, all right, so we have 10 correct answers, 13 incorrect, and many are absent, it looks like. All right, so let's look at this. All right, so here we know that dB is equal mu0 over 4 pi. The current I, current is the same, ds crossed with the unit vector r divided by r squared. Okay, so let's start with A. All right, so let's draw so the unit vector r is like this. Okay, and this is ds. So you can see that in this case the unit vector and ds are parallel. So the unit vector ds is parallel to r for point A. Okay, so this will give you 0, cross product of 0. Two parallel vectors will give you 0. Okay, let's take point B. So for point B, this is the unit vector r. Okay, it makes an angle of 90 degrees with the s. Okay, so this is a right angle. So for point B, we can see that this is mu 0 over 4 pi. Okay, ds crossed with r, so it will be the length ds with the unit vector. The magnitude of the unit vector is 1. Cosine of sine of 90 is 1. Sine of 90 degrees, which is 1, divided by the distance squared. So let's call this distance r. All right, let's do it for point C. So point C is, this is the distance here. So the unit vector is going to be like this. Okay, so you can see, let's call this R1 or RB. Okay, let's do it for C. So dB in this case is mu 0 over 4 pi. Okay, so it's ds times unit vector, magnitude of the unit vector, which is 1, times sine. This angle theta is less than 90, so sine of theta. Okay, so it's less than 1. Sine of an angle less than 90 is less than 1, divided by the distance is further away, so this is RC squared. So we can see, first of all, sine of theta is less than 1. Okay, second, RC is larger than RB, so the magnetic field vector at point C is going to be less than the magnetic field at point B. Okay, so that means the strongest magnetic field is at point B, then at point C, then at point A, which is 0. So the correct answer is B, C, and A. All right. So this is a checkpoint, and let's go to this problem here. Okay. So now we have an element or a line that is conducting current along the x-axis. So it's a straight wire of finite length carrying a constant current I and placed along the x-axis as shown in the figure. Determine the magnitude and direction of the magnetic field at point P. Okay. We did not mention how we determine the direction. Okay. To determine the direction, what we do, we use the thumb, point the current along the thumb, okay, and swing with the 4 fingers of the arm, and that will indicate the direction of the current. So let me show you how we can do that. All right. So for example, here, this is a current flowing through this wire. So you place your thumb in the direction of the current, and you swing your 4 fingers. The fingers will be swinging in the direction of the magnetic field. So if you are interested at this point, when you swing your finger, the magnetic field is going to be outside of the page. But at this point, when you swing your finger at this point here, it's going to be into the page. So this is how we can determine the direction. Very similar to right hand rule. Anyway, you use the right hand, you point your thumb in the direction of the current, you swing with your 4 fingers. The direction of the swinging is really the direction of the magnetic field here. So if you are here, when you swing, the magnetic field is like this. But if you're here, when you swing like this, the magnetic field is pointing towards me. If you're here, the magnetic field is pointing into the page. So this is how we can determine the direction of the magnetic field. Okay, so let's go back to this. All right, so here we are going to take, so we can write dB is mu 0 over 4 pi, the current I. Okay, we have an element ds. Let's consider this element here. So we have, this is ds crossed with the unit vector r, divided by the distance r squared. Okay, so let me go back to the presentation mode. I don't know, whenever I go to the presentation mode, it takes a long time. Okay. All right, so let's. All right, so the element ds crossed with r, if you do the cross product, if you bring the ds vector to the r vector, you find that your thumb is going to be pointed outside of the page, so the magnetic field is in the k direction. So and ds dr, notice that ds here is in the along the x-axis, so we can write it the cross product. So this is the angle here, phi. Okay, so if we write the ds, which is equal dx, sine of sine of phi is actually pi over 2 minus theta. You can see this is theta, this is phi, and this is 90 degrees. Okay, so sine of pi over 2 minus theta, which is equal to cosine theta. So you can see that this cross product gives us dx cosine theta times k. All right, so now we can write dB. dB is equal mu 0 I divided by 4 pi times ds crossed with r, this is what we are writing here, okay, divided by r squared. Okay, so now we're going to express dx also. Notice that r in this case is equal a over r is cosine theta, so r is equal a over cosine theta, and we can write r squared is just equal a squared over cosine theta squared. But also we can see that x over a is equal to minus tangent theta, because this is in the negative direction. So x is equal minus a tangent theta. So we can write take the derivative of this. Remember, the derivative of tangent is 1 over cosine squared. So dx becomes minus a 1 over cosine squared theta d theta. So this is the dx. If you take the derivative of this element, you get this element. So we're going to replace this here, okay, and we will integrate. Okay, so now this is now the equation. We replaced dx by this. We have a minus sign here, okay, and we replaced. So here we have cosine squared theta, because we have 1 over r squared, and r squared is a squared over cosine theta squared. So this becomes, so you can see here we have cosine theta squared cancels with cosine theta squared. We have a and a squared here. So we obtain that dB is minus mu 0 I divided by 4 pi a cosine theta d theta. This is not difficult to integrate. We can, after making the change of variable, now it becomes an easy integral. Okay, so minus mu 0 I divided by 4 pi. We are integrating from an angle theta 1 to theta 2. Okay, and so if I take minus inside, it becomes, instead of sine of theta 2 minus sine theta 1, it becomes sine of theta 1 minus sine of theta 2. The integral of cosine is sine, because the derivative of sine is cosine. Okay, so this is the equation that gives me the strength of magnetic field at this point. If I know the length of the wire from both sides, let's say L1 and L2, I can determine theta 1 and theta 2, and I can plug into this equation to determine the strength of the magnetic field. So notice again, it's proportional to the current, but notice something. Instead of being inversely proportional to the distance squared, now we have only a in the denominator. So it's 1 over a, which is this distance here. So it's different from the Biot-Savart equation. Now let's assume this wire goes from minus infinity to plus infinity. Okay, so when this goes to minus infinity, that means theta 1 is minus pi over 2. okay, and theta 2 is also pi over 2, okay. So we extend the wires to infinity, then we can write this. So sine theta 1 minus sine theta 2 is going to be sine of pi over 2 minus sine of minus pi over 2, which is 2, and we multiply in this equation and we get the magnetic field. So the magnetic field becomes mu 0 I divided by 2 pi A. A is a distance from the point, perpendicular distance. Usually we refer this to R, so usually we call this R, okay. So in many books you will see this written as mu 0 I divided by 2 pi R. So this is the magnetic field from an infinitely long wire. Obviously, in reality, we cannot have an infinitely long wire, but let's assume we have a long enough wire and we are determining the magnetic field at point B. So this is a very good approximation of the magnetic field due to a current flowing through this wire. Okay, so you can see it's proportional to the current. You double the current, you double the magnetic field, and it's inversely proportional to the distance, perpendicular distance to the wire. So this is the general equation, and again, in order to determine the direction, we use the right-hand rule. We curl our fingers, and it will be pointing in the direction of the magnetic field. So you can see that here, the magnetic field is out of the page, and in this location here, it's into the page. So it's going into the page. So it's going in a circular fashion around the wire. The magnetic field is so these are the magnetic field lines. You can see them. Let's assume the current is like this here. So these are the magnetic field lines. So you can see they have no end or beginning. So it's circular in shape. And so if you go away from the wire, you get a circular shape also, but the magnetic field is going to be weaker. So the same thing, it will be in the same direction, but with a weaker magnetic field. Okay, so let's draw this in a two-dimensional manner. So this is a current conducting the current to upward, and so if you look from the top view, this is the current flowing outside of the page. Okay, so if you point your thumb outside of the page and you curl with your 4 fingers, excuse me, why are you leaving? You have a class now? Okay. All right. So if you place your thumb in the direction of the current and you swing with your fingers, so you have, so here, the thumb is coming out of the page, direction of the current. If I swing at point P2, you can see the magnetic field is pointing down. But if I swing at point P1 with my fingers, the magnetic field is now pointing upwards. So if I have a point here, same thing. So it will be pointing in this direction. If I have a point here, it will be pointing in this direction. Okay, so this is the magnetic field, and let's illustrate it here. Okay, so this is a different view. So here, in this case, the wire is shown as going up, the current going from going north or in the plus y direction. Okay, and again, if you swing with your finger, the magnetic field here is coming out of the page. The magnetic field here is into the page. So, but remember, the direction is dependent on the location relative to the wire. So as we illustrated here, so it's not the same direction everywhere. Only if you take a line like this, so the magnetic field along this line will be always in the same direction. Okay, but it will be stronger as you get closer to the wire. Okay, but as you rotate this line, the magnetic field also rotates with it. So now we're taking the wire conducting current in the opposite direction, going down, and so let's do it here. So now the current is into the page. If you point your thumb into the page like this, and you swing with your four fingers, we see that at point P2 it's going to be upward, and hence at point P1 is going to be downward. At this point here it will be like this. At this point here it will be like this. Okay, And if we draw it in the other direction, this is the current going down, and we swing with the thumb. So here it should be into the page, and here it should be out of the page. So here it's into the page, and here it's out of the page. And again, so remember, it's always with the thumb pointing in the direction of the current and curling the 4 fingers to indicate the direction of the magnetic field caused by this current. Okay, so here we have a wire. Calculate the magnetic field at point O for the current carrying wire segment shown in the figure. The wire consists of 2 straight portions and a circular arc of radius A, which subtends an angle theta. So this is an angle theta here. This is a straight portion, and this is a straight portion. So if we want to determine the magnetic field due to element AA prime, we can see that the R vector, if you take an element and you draw the R vector, so this is the R vector here, for example, it's parallel to the length ds. This is ds here. So let's say this is ds. So in this case, this will be 0. Same thing for the element C prime, because if you take the unit vector R and the element ds, they are anti-parallel, so the cross product will be 0. So in this case, this will be 0. Okay, so let's do the magnetic field. Thank you. Let's do the magnetic field due to the circular element. So this is dB is going to be mu 0 over 4 pi I ds crossed with the position vector r, unit vector r, divided by r squared. Notice r is called a here, so this is a squared. Okay, so notice that at any point the unit vector and the element ds, they are perpendicular. So this is perpendicular, so sine of 90 degrees is 1, so this simplifies. We can write dB is mu 0 over 4 pi I ds, so this is ds, okay, and r is 1, and sine of t is 1, okay, sine of 90 degrees is 1 divided by a squared. Okay, so notice that the element ds is equal r d theta. ds is r d theta. Okay, so I can write dB is mu 0 over 4 pi I r d theta. Yeah, let me leave it as ds. Let me leave it as ds. I'll convert it later. So over a squared, the integral of ds. Okay, the integral of ds is actually the length of this arc. So this is going to be mu 0 over 4 pi I divided by a squared. The length, let's call it s, and s is equal r theta. Okay, so I can write that the total vector here b, the total magnetic field b at this point here O, is going to be equal to mu 0 divided by 4 pi I a squared, and s is r theta, and r is equal to a, so this is a theta. So the a will cancel here, and we obtain mu 0 divided by 4 pi I theta. Is it correct? Yes, I think so. Okay, mu 0 over 4 pi I theta, divided by the a. Okay, so now we can add all of the elements, since the other two elements are 0. So this is actually the magnetic field at the center O. Make sure I did not make any mistakes. Yes. Okay, so mu 0 I theta divided by 4 pi a. This is the general equation. Okay, so now for a full circle, if this makes a full circle, we can replace theta by 2 pi. Remember, always the angle theta has to be in radians. So this is, if I go for a full circle, theta becomes equal to 2 pi radians, and so the equation becomes mu 0 I times 2 pi divided by 4 pi a, which simplifies to mu 0 I divided by 2r. So this is if you have a circular loop, okay, full circle, and if you know the radius of the circle, you can determine what is the magnetic field at the center of this circular loop by using this equation, mu 0 times the current divided by 2 times the radius or the diameter. So this is a general equation for an arc of angle theta and a radius r. Okay, so you can use this general equation, mu 0 I theta. Remember, theta has to be in radians. Okay, divided by 4 pi r is the radius of the curvature, and sometimes they call it a. Okay, and if it's a full, you can do it for a half a circle. Theta becomes pi for half a circle. For a full circle, theta becomes 2 pi, and you can simplify it and get. In order to determine direction, we use the same method. So if we, for example, in this case, if you point your thumb, if this thumb, and these are the 4 fingers here, okay, if you swing with your 4 fingers, you can see that the magnetic field here is coming out of the page. Okay, so as illustrated here. Okay, so for a full circle, it becomes mu 0 I divided by 2r. Okay, and here we just wanted to show you the direction of the magnetic field lines. So this is a full circle with a current flowing in this direction, in the counterclockwise direction, and we're illustrating the magnetic field lines. So notice the magnetic field lines. The magnetic field inside will be pointing like this, okay? And notice the shape of the magnetic field lines. They are very similar to the shape of magnetic field lines due to a permanent magnet. With the north, so this is north here, and these are the south. So you can see that with a circular current or current flowing through a circular wire, I can generate a magnetic field very similar to the magnetic field that I can generate with a permanent magnet. And this is the very, very important, because now we can control this magnetic field. We can turn it off and on. While with the permanent magnet, you have to move the magnet away or close to the object in order to experience the magnetic field. Okay, so let's do this example here. So here we have a magnetic field due a circular wire loop of radius A located in the YZ plane and carrying a steady current I as shown in the figure. Okay, calculate the magnetic field at an axial point P at a distance x from the center of the loop. So this is the point P here. Sorry, oops. I lost my pen. All right, it's okay. So, so we're going to determine it at point P. So let's take an element ds as shown here in the figure. Okay, so this is the element ds. The r is the distance between the s and point P. The unit vector r is as shown. It has a magnitude of 1. And notice that the angle between the r vector and the y-axis is theta. And if you try to do the idea of pointing the current in the direction of the thumb and swinging with your finger, you can see that the magnetic field is going to be pointing in that direction, and it makes an angle theta, because this angle is similar to that angle theta. So notice that this can be broken into 2 components, an x component and a y component. Okay. The y components, they will cancel. If you take an element from the opposite direction, it will have a y component in the opposite direction. So only the x component will remain. All the y components, they will cancel. So if you take an element at the bottom here, the magnetic field will be like this, and you will have an element like this and an element like this. So this will cancel that one. So all of the y elements will cancel, and the x elements will add. And let's try to determine that. Okay, so this is the equation from it's mu 0 I divided by 4 pi ds crossed with r divided by r squared. R is the square root of a squared plus x squared. So r squared is a squared plus x squared. okay? And we need to multiply this by cosine theta, and notice cosine theta in this case is going to be equal, cosine theta is going to be a divided by r. A divided by r, which is square root, r is square root of a squared plus x squared. So now we replace, we are trying to determine only the x component, that's why we are multiplying by cosine theta, okay? So this becomes the integral. If we sum all of these elements, we obtain an integral. The constant will go outside of the integral, and it becomes mu 0 I divided by 4 pi times a divided by a squared plus x squared to the power 1.5, because this is we have to the power 1 and to the power 1/2 multiplied, it gives us to the power 1.5. And now we integrate over the whole length of the circle, so it gives us the circumference of the circle. The circumference of the circle is 2 pi times a, okay, and this is the final equation. So it becomes mu 0 I divided by 4 pi, mu 0 I divided by 4 pi, and well, we have 2 pi and 4 pi, we can cancel the pi's, and we have 1/2, so mu 0 I a squared divided by 2a squared plus x squared to the power 1.5, or 3/2. Okay, so notice what happens if x goes to infinity. If x becomes much larger than a, then this will simplify because a will become negligible, and we have x squared to the power 3/2, that becomes x to the power 3, and we obtain the following equation. So if we let if x is equal to 0, yes, if x is equal to 0, we get the magnetic field inside the circle. This is what we have seen before. But if x goes to infinity, or x much larger than a, it becomes mu 0 I a squared divided by 2x cubed. So so ignore the lower part because we are not going to be studying magnetic moments, unfortunately. So this is the equation we can use. So basically it's the equation that you can see here at the top. Even the mouse does not yes, so this is the equation we can use whether x is equal to 0, that will be inside of the circle, or x approaches infinity, you can ignore the a in that case. Okay, so what is the source of Earth's magnetic field? We said that Earth has a magnetic field. The magnetic field is very important. It protects us from cosmic rays, and the scientists, they think that what is causing the Earth magnetic field is charged ions and electrons circulating in liquid form. So these are ions and charged, basically atoms. They are circulating inside the outer core of the Earth. Remember, if you go deep into the Earth, it becomes molten. Everything becomes like a lava, and so it's the circulating of this lava, or this very viscous material. It will generate, because they are charged, it will generate the Earth magnetic field. Okay, so this is very similar to an example we did earlier. The magnetic field due to the wire element 1 is 0. Wire element 3 is also 0 because the r vector is parallel to the ds vector. And this element here, we can just use the equation. Since the angle theta is 90 degrees, we can use the previous equation, which is mu 0 I, the angle. In this case, we called it phi. Phi is equal to pi over 2 divided by 4 pi r, and it simplifies to mu 0 I divided by 8r. Okay, so we'll stop here and we'll try to proceed tomorrow. I have your quizzes, so if you want to, please.